Hello and welcome to the Maths 2 component of the online BSc program. In this video, we are going to talk about a process called the Gaussian elimination method. Using this method, we will be able to do a lot of things. So, in particular, we will be able to find the solutions to any system of linear equations in a very fixed algorithmic manner, and we can also use it to find the determinant of a square matrix, which we kind of saw last time, and we can also use it to find the inverse of a square matrix which is invertible. Okay. So, let us quickly recall what was our what we have seen before. So, we have seen the following methods to find the solutions of a system of linear equations Ax equals b. Namely, we have seen if A is invertible, then the solution is unique and it is given by A inverse b, and we can find the solution by either Cramer's rule, that was the first method we saw, and the other method we saw was to actually compute A inverse. To do this, we find the adjugate matrix and then we find A inverse b. So, these are slightly cumbersome methods because they involve a lot of determinant calculations, and finding determinants is a very resource intensive process. So, you have to do a lot of computation to find determinants, right, and here we have to find not just one, but several determinants, and that is how these processes work. So, compared to this, remember that if A is in what we call reduced row echelon form, then we can find the solution of such a system very easily. So, if Ax is equals b is the system that we are solving, and if A is in reduced echelon form, then we have the following procedure to find the solutions, and note that there can be many solutions now because A is no longer a square matrix, it could be a rectangular matrix. So, you find the dependent variables. So, these are the ones which correspond to the leading entries. So, there is a 1 in the non-zero rows, which appears at the beginning of the row, the first entry of the first non-zero entry of that row looked at from the left, that is the leading term. So, the column corresponding to that column, the corresponding variable. So, if the ith column is a leading entry, then xi is a dependent variable, and if the ith column does not have a leading entry, that corresponding variable is an independent variable. Okay. So, all those columns which do not have leading ones, those correspond to independent variables. And then how do we find our solutions? You plug in any value that you want for the independent variables and you back calculate to find the values of the dependent variable. Okay. And note that each dependent variable will appears in a unique equation. That is the advantage of the reduced row echelon form, and you can use that to back calculate and find the value of a dependent variable. And then all such values, for every such choice of values of the independent variables, we get a solution of our system Ax equals b. Of course, you have to, before we do all this, remember this is very important, that if there is a 0 row in your reduced row echelon form and the corresponding entry in B is non-zero, then this system cannot have a solution. Yeah, this was one of the things we observed, and we will use this as we go ahead. Yeah, so, this tells you all the possible situations. So, it tells you whether there is a solution. If there is a solution, it enlists all of them, and we are going to make use of this technique. So, we saw this 2 videos ago, and we are going to make use of technique along with what we saw in the previous video, where we took an arbitrary matrix and we used row operations, so elementary row operations, to reduce it to reduced row echelon form, right. So, we are going to put both these two together and we are going to solve an arbitrary system of equations Ax equals b. Okay. So, what are the contents of this video? We will study what is called the augmented system or augmented matrix for a system of linear equations. we will study the Gaussian elimination method to determine all solutions of a system of linear equations. Yeah, and here our system may not have the same number of variables as equations. So, in other words, your A could be a rectangular matrix, it need not be a square matrix. Okay, and finally, we will use this also, this is very brief, to compute the inverse. So, we will use this technique also to compute the inverse of an invertible matrix, of course, which is square. Okay, so what is the augmented matrix? So, let A x equals b be a linear system of equations. So, A is an m by n matrix. So, you have m rows and n columns. So, remember that the n columns correspond to the n variables and the m rows correspond to the m equations, and B is as a result the m by 1 column vector or column matrix of constants which appears to the right. Okay. So, any such equation, we have these three matrices A, x and B. A is m by n, x is a column vector or column matrix of size n by 1, and B is a column vector of size m by 1. Okay, so, we form what is called the augmented matrix of the system. So, this is a new matrix and it is of size m by n plus 1. So, there is a small typo here, namely that our n plus 1 should be in the brackets. So, you have m by n plus 1. So, the first n columns are the columns of A and the last column is B. Okay. So, this is how I define the augmented matrix of this system. Okay, and we have a notation for the augmented matrix, it is A to slash B. So, this is to remember that the first n columns are coming from A and the last column is coming from B. Okay, and we put this vertical line. So, this is just notation, and how are we going to write this augmented matrix? So, we will write this augmented matrix as follows. So, if my coefficients for the equation are a11, a12, etc. So, then I have a11, a12 all the way up till a1n. I put this vertical line here, a21, a22 up to a2n, and then I have am1, am2 up to amn. Okay. So, now this is my matrix A, remember, right. So, A came in the first n columns, that is what the definition says, and in the last column I have my vector b1, b2, bm. Okay. So, this is the augmented matrix for the system. So, it is a matrix with m rows, same number of rows as number of equations, and n plus 1 columns. Yeah, the n columns coming from the coefficients and the last column coming from the constants. Okay. Okay. So, what do we do with this augmented matrix? So, for the augmented matrix, let's first do an example maybe of an augmented matrix. So, here is my system of equations, 3x1 plus 2x2 plus x3 plus x4 is 6, x1 plus x2 is 2, 7x2 plus x3 plus x4 is 8. Okay. So, A is the matrix 3, 2, 1, 1, 1, 1, 0, 0, 0, 7, 1, 1. You might remember this from the previous video. So, we have already done the operation of row reduction on this matrix. Okay. And B is the column vector of the constants which are appearing on the right. So, that is 6, 2 and 8. Okay. So, what is the augmented matrix? So, you just take these two and you put them together, but you put a line in the middle. Okay. So, this line is just to be, it is not sort of part of the matrix, but it is something that you put to remember that on one side you have coefficients and on the other side you have the constants. Okay. So, what do we do with the augmented matrix? So, this is what the Gaussian where the Gaussian elimination method starts. So, you have a system of linear equations A x equals b, and Gaussian elimination is going to tell you how to get all the solutions of this. So, it will use these two things. First, it will use the augmented matrix, and second, it will use the technique of reducing to the row echelon form that we have reduced row echelon form that we studied in the previous video, and then it will use that for a matrix in reduced row echelon form. If I have something like Rx equals C, then I can find all the solutions. Okay, this is exactly the technique. Okay, so let's go through the steps. So form the augmented matrix. So we just saw what that was. Perform the same operations on this augmented matrix that were used to bring A into reduced row echelon form, right. So we know how to bring any matrix into reduced row echelon form. So if you take the matrix A, there is a series of steps, and it's an algorithm using which you can put it into reduced row echelon form. So you have to use elementary row operations. Okay. So you use the same operations on this new matrix that you used on A in order to put A into reduced row echelon form. So note that this new matrix that you have need not be in reduced row echelon form. Okay. And indeed that is the point. If it is not in reduced row echelon form at the end, then something special is going to happen, and if it is in reduced row echelon form at the end, then something else is going to happen. Okay. So let R be the submatrix of the obtained matrix of the first n columns. So you look at so after you do this process on A/B, so the augmented matrix, you apply all these elementary row operations. So in the end you will get another new matrix, which is again with m rows and n plus 1 columns. So you look at the first n columns, and that matrix you call R, and let C be the submatrix of the obtained matrix consisting of the last column. Okay, so the last column consists of C, and to keep track again of the first n and the last column, we will put a vertical line between them. Okay. So we write the obtained matrix as R vertical line C. And now this is the important part. Notice that R is in the reduced row echelon form. It must be, right, because you took A and you applied all the row operations on A, which we used on A/B, that we used to put A into reduced row echelon form. So indeed R is exactly the matrix that you got after you applied all those operations to reduce it into reduced row echelon form. Okay, so R is exactly that matrix. Okay. So what's next? So this is the main point. Okay, this is the crucial point, which is why the entire method works. The solutions of Ax equals B are precisely the solutions of Rx equals C. Okay. So what have we done? We have taken an arbitrary system of linear equations Ax equals B. We have performed some operations on this on the matrices occurring there. We have found two new matrices, R, which is of size m by n, and C, which is of size m by 1, where R is in reduced row echelon form, and when we take the corresponding system of linear equations Rx equals C, the set of solutions of Rx equals C is exactly the same as the set of solutions of Ax equals B. Now, well, if you think a little about what's happening, you can see that we are already done here. So from here I can finish off how to find the solutions of Ax equals B. Let's list out the procedure entirely. Form the corresponding system of linear equations Rx equals C. Find all the solutions of Rx equals C and hence of Ax equals B, right. So if as we observed, the solutions of Ax equals B are exactly the same as the solutions of Rx equals C. That was the punchline of the previous slide. And now, so if we find all the solutions of Rx equals C, then I know all the solutions of Ax equals B. And how do I find the solutions of Rx equals C? Well, R is in reduced row echelon form, so I have a concrete procedure to find these, right. So you find the independent variables and the dependent variables, and then you put the independent variables to arbitrary values, and then you back calculate to find the values of the dependent variables, right. We have done examples of this as well. We recall this right at the beginning of this video. Okay. So we have a very concrete procedure now to find the solutions of Ax equals B. So let's do an example. So you might find this is the same example that we saw earlier, where we put the system of linear equations into the we wrote down the augmented matrix of the system of linear equations. So now let's perform the Gaussian elimination method on that same example. Okay. Now if you look at this matrix on the left, right, just the matrix, just this part, the A part, right. So if you look at that A part, then that A part is exactly the matrix that we used in the previous video, which we used completely computed what was the reduced to echelon form for. And so you have to use those same steps over here. So we'll do it afresh, of course. So we'll do that afresh. Okay, so the first step is you get a 1 in the 1 1 place, because you start with the first column and then you try to get a 1 in that 1 1 place. So you do R1 by 3 and then you do R2 minus R1 to cancel all the zeros below. So this is what you get. And now notice what's happening here. We are not performing these operations only on the A part, we are performing it on the entire matrix. So that includes the B part, it includes the column B. So when we went from the first step, in the first step, the R1 by 3 was also applied on the column B, right. So you have to apply it on the entire row, not just the row of A, but the entire row. Okay. In the second step, we did R2 minus R1, and in R2 minus R1 we got a 0 in the second place of the last column, right. So we have performed this on the entire second row, not just the A part of the matrix. Okay, let's continue. So the next thing we do is we multiply the second row by 3 in order to bring a 1 over there. Then we cancel out the 0 below that 1 by doing R3 minus 7 R2. Yeah, keep noticing what's happening to the last column, right. We are applying all this on the last column as well. Okay, and then finally we have to get a 1 in the third row now. So we divide by 8, and notice that the 8 in the last column also got divided by 8 and we got a 1. Okay, so let's write down this matrix again, and maybe now I'll finish this calculation. So this is already, the matrix on the left is already in row echelon form. So now I'm going to reduce it to the reduced row echelon form. So in order to do that, what do I do? So I do R2 plus R3 and R1 minus 1/3 R3. Okay, so what do I get? So this is still 1 0 0, 2/3 1 0, then 0 0 1, and well, we are slightly lucky, we also get a 0 0 1 here. And then let's see what happens here. So R2 plus R3 means I get a 1 in this place, so I already have a 1 here, and then R1 minus 1/3 R3, so 2 minus 1/3, so that's 6 by 3 minus 1/3, so that's 5 by 3. Okay, and in the next step, what do I get? I do the same thing for the second column. So I do R1 minus 2/3 R2. So if I do that, I get 1 0 0 0 1 0, 0 0 1 0 0 1, but something may change here. So R1 minus 2/3 R2 means you have 5/3 minus 2/3. So 5/3 minus 2/3 is 3/3, which is 1. So 1 1 1. Okay, and this is my final matrix. So in terms of our notation, this is what I called R and this is what I called C. Now let's write down this corresponding equation. So we have Rx equals C, and now how do I find the solutions for this? So we look at the independent and the dependent variables. So here there is 3 leading ones, namely column 1, column 2 and column 3. So, x1, x2, x3 are dependent variables, and x4 is independent. So, let us put an arbitrary value for x4. Okay, so substitute x4 equals c, and now let us see what happens to the others. So, x1 actually there is no choice, x1 is 1, x2 again there is no choice, x2 is 1 if you write down the equation, and in the third equation we have x3 plus x4 equals 1, but we have put x4 equals c. So, that means x3 equals 1 minus c. Okay. So, the set of solutions of Rx equals c, and hence Ax equals b is vectors of the form. So, that is x1. So, you can either write it as a vector or or explicitly. Maybe let me write it explicitly. So, x1 is 1, x2 is 1, x3 is 1 minus c, and x4 is c. Okay, and where c can take any choice, right? We can have any number for c, so any real number, or I can write the same set as in terms of a vector as 1, 1, 1 minus c and c, okay, where c belongs to R. Okay. So, we have determined all the solutions of the system of equations Ax equals b, where A was exactly that matrix that we started with in our first example. Okay. So, maybe let us do another example. So, here we have x1 plus x2 plus x3 is 2, x2 minus 3x3 is 1, 2x1 plus x2 plus 5x3 is 0. So, the matrix representation, so A is square matrix 1 1 1, 0 1 minus 3 2 1 5, and B is 2 1 0. So, the augmented matrix, you put A and B beside each other and put a vertical line across them. So, it is 3 rows and 4 columns, where the fourth column is B and the first 3 rows are A. Okay. So, let us do this example maybe explicitly. Yeah. So, maybe let us write down the first step. So, this is R3 minus 2 R1. Why R3 minus 2 R1? Well, there is already a 1 in the 1 1th position. So, R3 minus 2 R1 cancels that 2 at the in the first column, and note that we have also applied this on the last column. So, the last column entry becomes minus 4. Okay. So, let us do one more step. So, you have R3 plus R2 now, because once again our so we want a 1 in the second column in this part of the matrix over here, which we already have, right. So, I do not have to do anything to make that 1, right, and now I want to use that 1 and clear off the minus 1 below that. So, to do that we do R3 plus R2, and again the entry in the third entry here changes. Yeah. So, let us continue and finish off this example. So, well, this is actually already in row echelon form. So, now let us put it into reduced row echelon form. To put it into reduced row echelon form, what do I have to do? I have to get rid of this 1 over here. So, let us do that. To do that, I have to do R1 minus R2. So, I have 1 0 0 and then 0 1 0, and then 1 minus 3, that is 4, and then minus 3 and 0, and then 1 minus 1, which is 0. So, 0 1 and minus 3. We could actually have skipped this step, but I am doing it just because I want to stick to the procedure. Okay. So, this is in reduced row echelon form. So, this is our R, this is our C. So, let us write down Rx equals C. So, R is in reduced row echelon form. So, I can read off all the solutions, and now you have to be slightly careful and carefully observe the following. Look at this last thing over here. So, you have a 0 row in the on the left, meaning in R you have a 0 row, but the corresponding constant is not 0. Yeah. So, as soon as that happens, what do we know? We know that this does not have solutions. Yeah, meaning there is no solution to this equation. Maybe that is how I should write it. So, there is no solution to this system. So, this system does not have solutions. Okay, and because this system does not have solutions, neither does Ax equals b. So, therefore, Ax equals b does not have solutions, right. And of course, what is Ax equals b? A is this matrix here 1 1 1 0 1 minus 3 2 1 5, and b was the column 2 1 0. Yeah, we wrote down the explicit system in the previous slide. Okay. So, we have shown an example where we can use this method to also check when a system does not have any solution. Okay, so, I hope both these examples have cleared up any residual doubts. I will just make a comment before I move ahead. I need not have done this last step. Any time in this procedure, when you hit this kind of situation where you have a 0 row and the corresponding entry in your constants, meaning on the other side of the vertical line is non-zero, we are saying that you have an equation of the form 0 times x 1 plus 0 times x 2 plus blah 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 0 times x n is equal to something non-zero. Of course, this cannot have a solution, and you can stop right there and say this does not have any solutions. Okay. But if you feel sort of uncomfortable with stopping in the middle, and especially if you want to program this into a computer, then you might as well finish the entire method. Okay. So, this is the power of the Gaussian elimination method. You can find out all the solutions of a system of linear equations. Okay. So, let us study a particular case. We have studied this in a previous video, namely the homogeneous system of linear equations. That means Ax is equals 0. So, remember that for Ax equals 0, we always have a solution, namely x equals 0, right. If you put each of your variables to be 0, then certainly this system is solved. So, 0 is always a solution. So, you can't have a situation where there is no solution for such a system. So, homogeneous system always has a solution. Okay. So, this is called the trivial solution. The solution x equals 0 is called the trivial solution. Okay. And of course, that also means that the other solution. So, if you have a solution which is not 0, meaning there is some xi which is not 0, then that is called a non-trivial solution. Okay. So, for a homogeneous system, there are only two different possibilities. One is that the 0 is the unique solution. So, remember that 0 is always a solution, whatever happens. So, if there is a unique solution, then it must be 0. Okay. So, 0 is the unique solution, that is one possibility. The other possibility is that there are infinitely many solutions other than 0. Okay. And how do we get this? Remember that if you have more than one solution, then you have infinitely many solutions. And why is that? That is because if you have more than one solution, then the only way to get that situation is if one of your variables is an independent variable, and as soon as you pick up an independent variable, you have infinitely many solutions, right. That's what we are saying. Okay. The other way of thinking about this is that suppose you have a solution, let us say, so you have Ax equals 0 and x1 equals let us say w1, x2 equals w2 and so on xn equals wn is a solution, then so is x1 equals t times w1, x2 equals t times w2 and xn equals t times wn, right. Because if you substitute x1 to be t times w1 etc. in a times x, then what will happen is the left hand side will be t times a11. Let us take the first equation. So, I have a11 x1 plus a12 x2 plus a1n xn is 0, right, and I know that a11 w1 plus a12 w2 plus a1n wn is indeed 0. But now, if you substitute t times w1, t times w2 and so on in that equation, then you will have a11 times t times w1 plus a11 times t times w2 plus a1n times t times wn. You can pull out the t common and then you will get t times a11 w1 plus a12 w2 plus a1n wn, which we know is 0. So, that is t times 0, which is 0. Okay. So, that is the other way of thinking about this. Okay. So, if you have a homogeneous system, that is something special. Fine. So, in a homogeneous system of equations, if there are more variables than equations, then it is guaranteed to have non-trivial solutions. Why is this? So, what is being said here? So, you have n variables, remember, and m equations, right. So, you have a matrix of size m by n, right, where these rows are corresponding to equations and columns are corresponding to variables. Okay. So, now if you have more variables than equations, then what happens? Then when you put it into reduced to echelon form, well, you have only m rows, right, but you have n columns and n is strictly greater than m. So, the leading coefficients, the leading ones can occur only in at most in m many places. So, there will be some columns which do not have leading ones. That means, there are some independent variables. Yeah, and as soon as you have independent variables, you will have an infinite number of solutions. So, in particular you will have non-zero solutions, yeah, so non-trivial solutions. In this video, we have studied the Gaussian elimination method, where we put together the fact that we can find the solutions for a matrix in reduced to echelon form, the coefficient matrix is in reduced to echelon form, along with the fact that any matrix can be reduced to echelon form using elementary row operations. Those were the contents of the last two videos, and this is a much more powerful method. It is far more efficient than the previous methods, even when your matrix A is invertible. So, this is a method that you will actually use in practice, and it is much more efficient. And even to compute the inverse of A, rather than computing all the minors and so on, this method is far more powerful. Also to compute the determinant, which we did in the previous video. So, Gaussian elimination method is the most powerful method we know in these contexts, and we have seen explicitly using it how to find all the solutions. We can check whether there is a solution at all, and then we can check which, once we know there is at least one, which of those are solutions. And finally, we have seen for homogeneous equations, that is for a homogeneous system, 0 is always a solution. So, the question is, are there other solutions, and we also know how to find those, again using Gaussian elimination. Thank you.